Ladies and gentlemen, my name is Zubov and I work at the Department of Chemical Engineering, University of Chemistry Technology, Prague, in the group of Professor Juraj Kosek. In this presentation, I would like to talk about discrete element modeling of colloidal suspensions, more specifically about the influence of spherical stabilization of these suspensions on their rheological properties. I will start with a short motivation for our work. The colloids we can define them as dispersions of small particles in a continuous medium. By small, we mean 1 to 1000 nanometers. And you can see here that based on the dispersed phase and on the medium where the particles are dispersed or the dispersed phase is present, we can talk about different systems which we can call colloids, like liquid, solid aerosol, foam, emulsion, and what I'm going to talk about today is a suspension. More specifically, I'm going to talk about latex, which is a colloidal dispersion of tiny polymeric particles, actually nanoparticles. They are used in adhesives, coatings, and paints. And what is extremely important is their stability, because if you buy a paint, you want it to be stable so that the particles don't coagulate, and you get a good product also, let's say, several months or years after you buy the product. From a polymer reaction engineering point of view, it is also important to understand behavior of these suspensions during their production, because as you can see in this picture at the bottom of the screen, sometimes during the reaction, the polymer particles, they tend to coagulate together, and then it is extremely important to remove such a coagulated product from the reactor. So this was basically starting motivation for the development of this discrete element model, which was carried out mostly by my ex-colleague Martin Kropa from our group. The outline of my presentation will be then following. I will start with the brief presentation of the discrete element method, its history, and how it is reformulated for the use in colloidal suspensions. Then I will talk about stabilization of by two methods, electrostatic and spherical stabilizations. And then I will talk about the results of our model and the model itself, which is focused today on the rheology of sterically stabilized colloidal suspensions. Discrete element method is a numerical method that allows simulation of motion and rotation of large number of particles. It's been actually developed almost 50 years ago for the use in rock mechanics, but later it's been adopted in many applications, mainly dealing with powder and granular matter and crack propagation simulation. In DEM, particles are characterized by their position, size, and velocity, and possibly also angular momentum, which means the rate of their rotation. Trajectories of the particles are then calculated by integration of Newton's second law of motion. What is great about DEM is that it's very versatile with respect to the forces we can implement in the model. For instance, frictional forces, gravitational, elastic plastic collisions between the particles, their adhesion, or electrostatic forces, and many others. In colloidal suspensions, we have some specific interactions between the particles, so that we have to account for different forces, like, for instance, lubrication forces between the particles, electrostatic repulsion, and van der Waals attraction, which form together the so-called DLVO theory. And then we have elastic repulsion and van der Waals adhesion, which create the so-called JKR theory. That is a theoretical mathematical description of contact mechanics of the particles. We have also particle-fluid interactions, because the fluid in our case is typically water, where the small particles are dispersed. There we have a drag force acting on the particles, and of course the particles, how they move and they rotate, affect the fluid back. So in a way, we have really unique combination of non-contact and contact forces together with computational fluid dynamics that has been developed in our group, and we are still continuing developing. When the particles are placed in the solvent, the functional groups in the material from which the particles are created, they begin to how to say, interact with the solvent molecules, and partially dissociate. That leads to the formation of charge inside the particle. And if you look at the picture, you can see negatively charged particle. So for instance, if the particle is charged negatively, then it will, of course, attract positively charged molecules from the solvent. And the positively charged molecules of the solvent will, on the other hand, attract negatively charged molecules. So this surface charge present on the molecules leads to the so-called electric double layer. What is important about this slide, about this explanation, is that when the particle is actually surrounded by a dominating charge, then it leads to the stabilization of the particles, because two particles that are surrounded by positively charged ions will be repulsed from each other, as we can imagine. Then typically in colloidal systems, we have to account also for attraction of the particles by the so-called van der Waals force. And if you look at the graph on the right-hand side, you can see that the van der Waals attraction has a negative values below zero. That means that all the time it is actually attracting the particles together, but its magnitude is actually quite low and effectively zero on the higher distances between the particles. While on the other hand, electrostatic repulsion is always that means it has positive value, and if you sum these forces together, you get the so-called DLVO potential, or DLVO theory, that is very famous and describes basically the fundamental interactions between the particles. So it is the DLVO potential basically represents potential or energetic barrier between the particles. So the barrier can be overcome when the particles have enough, let's say, for instance, kinetic energy, so that they can actually fall into the van der Waals attraction regime on a very short distance, and then they can coagulate. On the other hand, spherical stabilization is caused by adding a special stabilizer molecules into the solvent. The stabilizer we can imagine as a relatively long polymer chain molecules that have a very complex interaction with particle surface, with the solvent, and with each other. So these stabilizer chains, they can be bonded to the particle surface. They can form a permanent bond. That means that they can be grafted, chemically sorbed on the surface, or the bond with the particle surface can be only temporary. That is called physisorption or absorption to the surface. In the spherical stabilization, we have repulsive forces. That means elastic interaction between interacting stabilizer chains. As the particles get closer to each other, the stabilizer chains, they tend to repulse each other, of course. And the other repulsive force is the osmotic repulsion, which is caused by the lower concentration of solvent molecules in the stabilizer layer of two particles that are in close contact. So the solvent actually tries to compensate for this low concentration and flows in between the particles causing them to move apart from each other. But we have also attractive forces like bridging, for instance, where one stabilizer chain can be actually adsorbed to two different particles, making them coming closer to each other, or the depletion force, which is a kind of anti-osmotic effect, but the depletion force acts only on very, very short distances. What is a very interesting and challenging topic from scientific point of view, and actually is the core of my presentation, is the relation between the spherical stabilization and the rheology, that means viscosity of these stabilized dispersions or suspensions. It is, as you can imagine from the description of the forces, very complex problem, and it lacks a rigorous theoretical description. That means we can use only semi-empirical models, or so far in the literature, the semi-empirical models have been used for the estimation of the rheology of such suspensions. That was actually a good motivation for us to try to use the discrete element method. So far, our model has been based on the DLVO theory. That means it considered only electrostatic or ionic stabilization. So the extension for spherical stabilization was necessary. And also we need experimental data that we can compare with our simulation results. That means at least suspension viscosity measured at high shear rates. Why high shear rates, I will explain in a second. So our model is, as I already mentioned, based on the integration of second Newton's law for the trajectories of the particles. In this Newton law, we have the summation of forces that act on each particle, and we assume only pairwise interactions. Particles are characterized by mass, velocity, and angular momentum, and position as well. I have a mistake here, small mistake. And then forces that we assume in our model are flow interactions between particles and the solvent. So it's two-way coupling between our code, our in-house code developed describing the DEM model, and the public domain software called OpenForm that describes the fluid dynamics of the solvent. Then we have lubrication forces, contact interactions described by JKR theory, and non-contact interactions that describe the spherical stabilization. On this slide, you can actually see that in the spherical stabilization model, we assume three different forces, the depletion attraction, osmotic repulsion, and elastic repulsion, which have to be summed together to get to the overall potential acting between two particles. As you can see on the right-hand side, the model is also using many different parameters. Some of them are more certain and easy to get their numerical values. Some of them are less certain, which have to be somehow estimated from some semi-empirical or purely theoretical correlations. And there is one uncertain parameter that is called volume fraction of stabilizer on particle surface. That means actually how dense is the number of the chains that are on the surface. That is of course related to the concentration of the stabilizer in the solvent, because if we pour the stabilizer into the solvent, some of the molecules will tend to stay in the solvent, some of them will tend to adsorb on the particle surface. Therefore, with higher concentration of the stabilizer in the solvent, we will get higher concentration on the particle surface. There must be some kind of adsorption isotherm which we have to add to our model, and we are working on it right now. The computational domain actually assumes a simple shear flow between two parallel plates. The bottom plate is stationary and the upper plate moves with velocity u, which we set. With this, we basically get velocity gradient in the fluid and cause the particle to move. The number of particles in the domain is around 5,000, which we typically use. And the model can calculate so far only relatively high shear rates. That is both advantage and the drawback of the model. The advantage is that at high shear rates we can neglect the Brownian motion of the particles, which makes the model easier for numerical handling and integration. But on the other hand, it is very difficult to get experimental data measured at really high shear rates. So this is a drawback, and we are currently working on the parallelization of the developed code so that it can become much more computationally faster, because what we need to simulate lower shear rates is actually more time or more computational power. So from this arrangement, we can actually evaluate from the obtained velocity field in the fluid, we can actually evaluate the viscosity of the suspension. And there are some results here that I can show. These are more qualitative, but there is on the left side, there is a 20 years old actually measured potential in between the particles, depending on the thickness of the hairy layer, that is the stabilizer layer on the particle surface. And on the right hand side, you can see a prediction from our model. So it is natural that with the increasing chain length of the stabilizer, that means that the hairs that are let's say the so-called hairs that are absorbed on the particle surface are longer. If they are longer, then the potential, the repulsive potential, becomes more and more steeper. That is more or less qualitative agreement with experiments. And of course, when the hairy layer around the particles is becoming more and more thick, we are getting higher suspension viscosity, which is still in a qualitative agreement with literature and experimental data. If we increase the stabilizer concentration, here we follow the volume fraction of stabilizer in the layer. We again get increase in the viscosity, because with increased stabilizer concentration and also chain length, the particles become somehow harder. That means they increase their effective volume, which can explain the increase in the overall suspension viscosity. If you want to validate the model, we basically managed to, by the cooperation with our colleagues from San Sebastian, we managed to get experimental data measuring viscosity of the suspensions at very high shear rates. So basically, the black points in this graph are the experimental data, and the red squares are the values that we get from our model. As you can see, we have some kind of system. They measure the dependence of the viscosity on the concentration of stabilizer in the suspension, and at these settings with this particle volume fraction, that means the concentration of particles in the suspension 25%, we get we quite actually a little bit disagreement with the experimental data. But if you look at the predictions for particle volume fractions 45%, we actually get quite a good agreement also for different particle radius. So we believe that if we establish a good, let's say, theoretical foundation for the estimation of the concentration of stabilizer in the layer surrounding the particle, and also if we manage to parallelize the model so that we are able to calculate lower shear rates of the suspension, then we will be able to fully validate the model and get to purely theoretical first principles predictions, not based on empirical relations. So to conclude my presentation, discrete element method is versatile and robust approach to the first principles modeling of various phenomena in concentrated colloidal suspensions, such as coagulation of primary particles, particle fouling on the reactor or equipment wall. We can investigate the particle agglomeration and morphology of the agglomerates that are formed, dynamics of gelation, and also we can predict the rheological characteristic of the suspensions, which was topic of my presentation. DEM model describing ionically stabilized colloidal suspensions has been extended so that now it accounts for spherical stabilization, and the first results of suspension viscosity predictions are in qualitative and partly also in quantitative agreement with available experimental data. With this, I would like to thank you for your attention, and if you have any questions or would like to discuss more the results in our model, please let me know on my email, which you could see on the first slide of the presentation. Thank you for your attention.